Good morning. We begin lecture 46. This is the last two lectures or probably three lectures on CDMA. Some very important concepts that we want to cover. One is the concept of the rake receiver and how does CDMA also work, the method by which it achieves the performance in a multi-user environment. There's a lot of similarities, so the framework that we developed for the Multipath will also be useful in our understanding of the multi-user. So we will try to keep both those, they are not distinct, keep them as two pieces that are tightly interconnected. So by way of a quick review of yesterday's concepts, one of the things that we have studied is the role of M sequences. M sequences are used quite extensively for scrambling. We have seen that as several different places where it is used for scrambling, and so it is useful for us to know its properties. The key properties that we leverage are the following: that if I had basically the shift property. If I add a M sequence with a shifted version of itself, so basically cyclically shifted by n times. So this is the notation that we have been using for the following. So this basically stands for B of n plus k mod q, where q is the length of the M sequence, and we said that this is equal to another shifted version, and we will actually see that this property plays an important role in today's discussion. So this is one of the properties of the M sequences. Another very useful property of the M sequence is the cyclic correlation. Rx of k defined as 1 over q summation L equal to 0 through q minus 1, x of L, x star of L minus k mod q, and we showed that this is minus 1 by q using the shift property. And again, these are linked and useful for us to remember because this property comes into play in several places. Maybe it's good for us to mention right here that we have used both the representations of M sequences. For example, this property is based on the binary representation because you're doing modulo 2. This property, the way we have written it, is based on the bipolar. So a 0 mapping to a 1 mapping to a minus 1. So, or in other words, x of I is equal to 1 minus 2 times the corresponding bit value. Okay, so we have used both the representations. So please always before you apply something, say, okay, am I working in binary or am I working in bipolar? That's just an important part to keep in mind. I meant to ask a question. We use the word scrambling. Is scrambling different from encryption? Okay, I see several nods. What is the difference? Scrambling versus encryption. Okay, the point that was mentioned was scrambling means that the order of the bits has been changed. Okay, in our notation, particularly the way it's defined in cdma2000, scrambling is slightly different. Basically, you do a modulo 2 addition with another sequence. So basically, you have the original sequence and a modulo 2 addition. So let me just write that down. So if I have what I call a message sequence, in the case of CDMA2000, it would be 1.2288 megachips per second. Then to me, the scrambling operation actually turns out to be a modulo 2 addition with a sequence, M sequence in the case. So it's again in the binary form. This is also at 1.2288 megachips per second and comes out a modified sequence which is also at the same rate. Okay, so we can make the following statements that scrambling is a bit level operation. is a bit level operation. You input in one bit, you get another bit. So yeah, we do use the word scrambling to change the order also, but in the context of the CDMA systems, the scrambling that we are talking, scrambling in our context is to make the data look random. So it is more than just a shuffling of the order of the bits, it's actually doing a modulo 2 addition. So it's a bit level operation. Notice the input and output rates are the same, so it's very important to note that it does not increase bandwidth. So scrambling does not increase bandwidth. Okay. Now the purpose of scrambling is to make the data look random at the physical layer. Scrambling is a physical layer phenomenon. Encryption, on the other hand, is not necessarily a physical layer phenomenon. You basically want to be able to hide your data so that somebody else cannot receive it. So usually encryption is done at the higher layers. It's usually done at the application layer. Whatever is the data that you get, you want to represent it in some other way. So encryption also does not increase bandwidth. Usually our algorithms, if you give a 128-bit sequence, will produce for you an encrypted 128-bit sequence. So encryption also does not increase bandwidth. But keep in mind, it has a very different purpose than the scrambling that we have done. Okay? Because undoing the scrambling should be very easy, because once you know the M sequence. So the reverse operation is easy, that is for scrambling. Yes, reverse operation is very easy. If you know the M sequence, you just do whereas for the encryption, you want the reverse operation to be as hard as possible. Okay, so there is a fundamental difference. Reverse operation, you want to make it as difficult as possible, so that unwanted user may not have access to the information. Okay? So these two are similar. Now the only bandwidth expanding operation that we have in the CDMA system, bandwidth expansion, comes only through the spreading process. Yeah.
So even in encryption, you only want the reverse operation to be difficult for the one who does not know the key, and yes, for the one who knows the key, or in this case the spreading sequence, M sequence.
So basically it's the reverse operation is difficult for everyone other than the desired user. That is correct, yes.
Same with the M sequence also. No?
Well, M sequence is, as you know, it's very easy to find out once you know the feedback taps. Usually, in the case of CDMA, the M sequence is actually published. It's in the public domain. Okay, so basically it's a matter of waiting for you to synchronize with the M sequence. So the scrambling part is something that anybody can do. The descrambling part can do. But the encryption is done at a higher layer. It's done with some secret information. All the information about the encryption algorithms usually are not published. So there are some secret information. So again, to that extent, the scrambling operation has a very definite goal. It wants to make the data look random, make it look like white noise. So sometimes you may have a string of zeros. You may not want that to come as a string of zeros in your sequence. So scrambling will make sure that any string of zeros gets sort of modified. So like that, the bit level operation of scrambling makes the data look random. Encryption, the intent is not that at all. I mean, it has a very specific thing of hiding the user information. Okay, so bandwidth expansion comes primarily or solely from the spreading operation. Okay, so there is spreading, there is encryption, there is scrambling. Encryption is something that we have not touched upon. It's basically it's a part of digital communications that happens at a higher layer. What we have been focusing on has been bandwidth expansion through spreading, and we've also been looking at scrambling as a way to randomize the data, also protect us against some elements of multipath as well. Okay, let me just, if I gave you a irreducible polynomial, I tell you that the following is an irreducible polynomial: 1 plus x squared plus x for power 5 plus x power 6, and I ask you to generate and tell you that it's a maximal length sequence. You should be able to connect the feedback taps and actually generate one period of the sequence. So this is a sixth order polynomial. So if I want to implement it, I must have 6 shift registers. I can rewrite the polynomial in terms of delays, and please make sure the connections are done correctly, otherwise you will not, it may not be a maximal length sequence. So the output of the first delay is taken. These are all modulo 2 additions that you have to do. It's in the binary representation. Second delay is also taken. So this is delay, 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 delay. Then I don't need the output of the third delay, fourth delay, I need the output of the fifth delay and the output of the sixth delay. This output is the sequence, and this tap actually is the feedback tap. That's so 1 equal to x plus x squared plus x5 plus x6 is the feedback connections. You can start with any starting state, does not matter, and you'll basically the sequence will repeat itself. So we should get a 2 power 6 minus 1. In this case 63 sequence. Don't do it by hand, it's not, I just want you to make sure that you are able to do that. Okay, another point to reinforce from our discussion yesterday, difference between CDMA2000 and wideband CDMA. The chip rate that we were using is 1.2288 mega chips per second. All channels must have this chip rate. The occupied bandwidth of the CDMA2000 signal is 1.25 megahertz, so that's how the channelization is done. The channel that is of most interest to us is a traffic channel. Traffic channel originally designed to be primarily voice, so it takes in voice, encoded voice or compressed voice at 9.6 kilobits per second, and then as you know it does the rest of the processing. The first stage is the convolutional coding that it does, it makes it 19.2 kilobits per second. This is the convolutional coding. The next step is the spreading. Q is equal to 64 is the spreading factor that we use, and it is one of the codes from the Walsh 64 length Walsh-Hadamard sequences, and this basically gives us this is the spreading operation. So there are 2 stages of bandwidth expansion. Coding also expands the bandwidth, spreading expands the bandwidth, both, and eventually we get to 1.2288 mega chips per second. If somebody wanted more than 9.6 kilobits per second, you would have to give them multiple spreading codes. Now on the other hand, wideband CDMA has a chip rate which is 3.84 mega chips per second in an occupied bandwidth of 5 megahertz, roughly 4 times the bandwidth of the CDMA2000 system. 4 times the bandwidth should approximately scale to 4 times the capacity, because that's how the systems are designed. So in this case, the spreading factors are not from the Walsh-Hadamard family, but they are from the OVSF set. So OVSF set, OVSF L comma N represents the nth code of length L. Where length L can be either 2 squared or 2 cubed, 2 power 4 dot dot dot. In wideband CDMA, there is a provision to vary the spreading factor all the way from 4 to 512. So very high spreading factors to very low spreading factors. But most commonly 512 is not used, so it is from 4 to 256, but still it has a larger spread. Okay? And it's 3.84 mega chips per second in 5 megahertz. We also made an observation, if you remember, that CDMA2000 does power control power control at the rate of 800 hertz or 800 times per second. It tells you to go up or down. It tells the users to go up or down. So in other words, it's 800 adjustments per second. Okay. Now here is a question which will indicate, I want you to have an intuitive feel for CDMA systems. And if you can answer this question, it will be very helpful for the entire class. So the question is the observation is the following. Wideband CDMA does power control at the rate of 1500 times per second. The question is why? Why did it have to do more than the number of times as CDMA2000? Can you think of any reasons? There are at least two very important reasons.
More number of users.
Okay, very good. First answer was more number of users because it's a 5 megahertz system. You have more codes available, more users are present, and if one of the users is using excess power, then it will affect lots of users. So you don't want to take a chance. So you want to control that. So first one is the fact that it is wider bandwidth, which means more users, and if one of the users is using excess power, it is going to affect a lot more people. So you want to have a tighter control. Okay. One more reason. This will really tell me that okay, you have fully understood the CDMA part. The answer is there on the slide. Answer is there on the slide. What protects you against multi-user interference?
Spreading.
Is your spreading factor. In wideband CDMA, there are some users who are running at spreading factor of 4. They don't have much protection. Why are they using spreading factor of 4? Because they have lots of data to send. Okay. Now, if they have less protection against multi-user interference, so if there is somebody else who's transmitting with more power, they can actually kill these users. So you want to control these users. So typically in a wideband CDMA system, somebody with spreading factor 4, because he does not have much processing gain, will be transmitting with higher power than the one who is using spreading factor 256. Is that correct? Does that make sense? Because he's got more data to send, you have to use more power to get your data across, right? And if it's so, one is if somebody else transmits with more power, you don't have much protection because you are using only spreading factor of 4. Now the second user, if you use more power, what will happen? Already you are at higher power. If you use more power than you need, you are going to affect others as well. So the fact that you have more users, the fact that you have some users with less spreading factor who are transmitting at high power, it's a interaction. So a second reason would be maybe just to say that yes, there are low spreading factor users, and they actually complicate the system because they have less protection against interference because their spreading factor is low, but they also are transmitting with higher power. Less protection against interference. So again, once you understand CDMA at an intuitive level, it starts to become very, very interesting. So they are transmitting low spreading factors, they are transmitting with higher power. Transmitting with higher power, so you want to control them more tightly with higher power. Okay, so everything that you have studied in digital communications is embedded here. It's just that just have to make sure that you catch those interesting elements. Okay, yesterday we did the OVSF. We will not repeat that except to go through and fill in the last column. If you had assigned 128,127 instead of 128,2, you should get the following codes. Does not affect the length 256 codes, does not affect the 128 codes. Okay, but it starts to affect the lower value. It doesn't affect the 64 as well, because if you go through and do that, but it does affect the lower spreading factor codes 30 and only 2 are available from the spreading factor 4, because this particular code 128, 127 comes from a different parent from the, if you go back in the OVSF tree. And so it does not affect the number of successors, but it affects the number of earlier codes or predecessor codes. And this is an indication that if you don't do your code assignment properly, you actually can affect your capacity. So there is some concept or understanding of something called code reassignment. Okay, for optimization of the performance, you can do a code reassignment and say, okay, no, instead of using spreading factor code number 127, start using code number 2. And user says, it doesn't matter to me, I can use any code, it's not a problem. So once you do that, you have more codes available in the system. So there's an interesting optimization that can be done if you, what you do call pack your codes, so that you minimize the number of predecessors. So that way you have more flexibility in the assignment of codes. It's an interesting one. I'm sure you will see the pattern. Okay. One of the classical CDMA systems, I always wish that my students will have a understanding of history as well as from the past as well as to the present. So a few minutes on the history. So classical direct sequence spread spectrum systems for multi-users. Okay, multi-user, not single user. So this is when did this first come? cdma2000 came around the year 1996 or 1997. You can look at the dates on the slides. But almost 30 years earlier, this was already proposed and actually demonstrated. So the credit goes to 2 people, Kasami in 1966 and to Gold in 1967. Okay, so they came up with a scheme which pretty much said you can use direct sequence spread spectrum for a multi-user environment. And so basically what they were going to do was propose codes. And the scheme was very simple, but having understood the scheme, I want you to be able to say, oh, I know that. I would have, this is nothing surprising. I want you to get to that point. So basically they came up with something called preferred sequences. Okay, preferred sequences. Keep in mind it's a multi-user scenario, and they are trying to design a system where you have good correlation properties between the codes. So preferred sequences. So they showed that there are pairs of M sequences, sets of 2 M sequences, which have a very unique property. Sequences have a unique property, and this unique property is that when you try all combinations of shifted versions of these 2 M sequences, the cross correlation can take only 3 values. So they have a unique property, and that unique property is a 3-valued cross correlation. 3-valued cross correlation. Now again, how this comes about and how to identify these sequences is not the important point. That they showed that such pairs exist, and the cross correlation turns out to be the following. So if they are length M sequences, the length will be 2 to the power of M minus 1. So that's your scale factor. The cross correlation can be -1. That means these 2 codes are perfectly orthogonal to each other, as close to perfectly orthogonal. Or it can have a value which is given by a function T of M. I'll define T of M in a moment. Or it can be T of M minus 2. Okay, these are the 3 values, and they showed that this function T of M is 2 power M plus 1 divided by 2 plus 1 if M is odd, and it is equal to 2 power M plus 2 divided by 2 plus 1 for even M. Okay, this is what was proposed, and they basically said that they would generate, if you have 2 M sequences, One is the generation of M sequence number 1, A, this is the second M sequence, this is B, and basically they said using this combination of preferred sequences that they would generate for you a set of codes that will give you good performance. Okay? And this was one of the absolutely remarkable results, because all it said was, you have now a large family of codes which have good cross correlation. Basically, just so that you get a feel for the numbers, if you take m equal to 10, so it will be 1 by 1023. What are these correlation values? It is -1, it is minus 65 or plus 63. Okay, so 65 by 1023 is 0.064. This is a reasonably low cross correlation. So what we are saying is that Kasami and Gold came up with a set of sequences which guaranteed you that the cross correlation is going to be good. So which means that you could use them for their. So basically now we look at and say, well, how good was this result, and some insight into that. So first we need to know how these Kasami Gold sequences were generated. So KG sequences where they said, okay, take A and XOR it with B with all possible cyclic shifts. Okay, and of course you can get 2 power m minus 1 cyclic shifts. Okay, so this basically will give you 2 power m minus 1 combinations. Basically, A is a sequence of length 2m minus 1, B is a sequence of length 2m minus 1. They're saying try all the cyclic combinations. Then they said you can also take A as one of the sequences, so it becomes 1 plus 1, and then you can take B also plus 1. So it is 2 power m plus 1. Okay? And the guarantee was this does not have the same confusion between multipath and multi-user. So two things that I would just like to quickly work with you. One is, first of all, the property. Why is it that if I have just two sequences and then I do cyclic shifts, how is the property preserved? Okay, let's do that, because once you do that, then you appreciate the rest of the. So let us take any two sequences from the Gold Kasami set or Kasami Gold set. Let me call the first sequence as D. It is A, the first M sequence, plus exclusive OR with a cyclically shifted version. Let me call that as BL, B sequence cyclically shifted. The sequence E is A exclusive OR with BM. Okay, so these are the two sequences. Now we need to find out the cross correlation between D and E. So this would be 1 by Q summation Q is equal to 0 to Q minus 1. I can write it in one of two ways. I can write it in the bipolar form, or I can write it in the binary form. The binary form is easier for us to work with, and if you don't mind, I will skip the first step of writing it in the bipolar form and go directly to the binary form. The binary form says 1 minus 2 times D of Q exclusive OR with E of Q plus K mod Q. Okay? So this is the correlation. I believe we have derived this similar expression yesterday while proving the property. So I will skip the unnecessary steps. Okay. Now, before we get to the further parts there, what is the guarantee of the Kasami gold? Basically, they said that the preferred sequences RAB, right, are such that they have the property 1 over q, and it will take on one of these values. It is -1 minus t of m or plus t of m minus 2. It will take one of these values. So this is what is the property of the preferred sequences. So this is at the background, preferred sequences, and in the process we have generated D and E through the mechanism shown by or defined by Gold-Kasami, and we are trying to verify that that these codes also have the same property. Okay, we're just trying to verify that. Okay, it's actually one step, and then we are through with the answer. So substitute for D and E. So we get 1 over q summation q equal to 0 through q minus 1, 1 minus 2 times d of q is a plus bl. A of q exclusive or with bl of q. Okay, that is d of q. Then have exclusive or substitute for E. E is q plus k, use a different color, A of q plus k. Remember that this has to be interpreted modulo q, exclusive or the second one will be Bm q plus k. Okay, just substitute it. The D and E were defined by the Gold-Kasami structure. I want to compute the correlation between D and E. You first write it in the bipolar form and then translate it into the binary form. I just wrote it straight in the binary form. The binary form can be related to the original sequences A and B in the following fashion. So now just one step, look at the combination of the two A terms, the combination of the two B terms. Okay. What can you tell me when I add two M sequences? So shift property will give you a third sequence. So this one can be written as 1 by q summation q equal to 0 through q minus 1, 1 minus 2 times, let me call that as A of q plus I, some other shifted version. Okay, it's not the original 2. And this will be exclusive OR with the B's also are a M sequence. If I take two cyclically shifted versions, it's going to produce for me another cyclically shifted version. I'm going to call that as B of q plus j. Okay? What did the property of the preferred sequences tell you? Any shifts of the original two sequences A and B has to be one of these three values. So you can then say, oh, these are just two cyclically shifted versions. One is cyclic shifted version of A, other cyclic shifted version of B. So this is RDE. This should also have the same three values. Okay. So basically, the whole set that you have been able to generate, a large set, 2 power m plus 1. Of course, now you can take the special cases of when it's only A. Remember, you have the option of choosing only A or only B. You can try replacing D with A and then D with B and show that it's exactly the same thing, the same argument, and you get the result exactly like before. Okay. Independently, I would like you to verify that RDE, this would be RDE, the argument is K, that's what is shifted. RDE of 0, I would like you to verify, will come out to be minus 1 by Q. It's that basically gives you the, so you can please check that out. Okay. Now let us ask this following question. Is the Kasami gold sequence set, is that something that would have been obvious to you, having studied what you have already studied? Let's go back and look at this. what did we say was the drawback of using M sequences for multi-user environment? The different shifts are the different M sequences, and we cannot differentiate between multi-user and multipath. Now, what did we do in cdma2000 to differentiate between multi-user and multipath? Scrambled it. What did Kasami, what are they doing? Scrambling. Because what are they doing? B, with all its cyclic shifts, gives you all the possible sequences. And what is A doing? Scrambling. So that's the secret. So this guy is the scrambler, and this one are the codes. And it turns out that you can use A itself, the scrambler itself, and you can use B, that's one of the option by itself without the scrambler. And because A and B are anyway have good correlation properties, they also satisfy the properties of the rest of the group. So again, once you have understood that M sequences are very good at scrambling, then you go back and look at it and say, at that time it was absolutely amazing. You know, you come up with a simple structure and it gives you 2 power m plus 1 codes. And then now you look at it and say, well, you know, it's okay, I understand. It's codes, I cannot use M sequences directly, I have to scramble them. And that's the answer. But you cannot scramble with any sequence. You have to scramble it with a preferred sequence, and that maybe we should still give due credit to Kasami and Gold. Okay, that's as much as I want to focus on the codes part of it. There is a very important element that you have to study and keep in mind as far as codes are concerned. But we are building practical systems, so let's move on. We have to look at two things. One is multipath, and then the other one is multi-user. So let's quickly set up the framework for multipath and then see how to. So we have a time varying, time dispersive channel. No problem, we know how to characterize that. So we will describe this as a multipath time dispersive, time varying channel. Okay, remember we have the 3-dimensional graph which we draw, and so this is not this is very familiar to us. Time dispersive, time varying channel, that is represented by h of t comma tau. T is the time variation, tau is the delay dimension. Okay, so given that we have this framework, what we are going to do is skip several steps and ask you to recall that in digital communications, based on your baud rate, that is your symbol rate, you have something called a symbol spaced equivalent channel. Whatever was the channel between the transmitter and receiver, you have something called a symbol spaced equivalent channel. Okay, symbol spaced equivalent channel, and that is what you will use to derive your equalizer structure. So again, it is basically it is equivalent to taking whatever channel that you have and resampling it at symbol space. So then it becomes easy for us to represent. So basically, then you can represent it as in terms of a discrete time channel model. So symbol spaced channel model. It is a discrete model, discrete time model. Okay, so you can represent your channel as some digital filter. Okay, so in effect, this is a digital filter. Okay, so what we can do is I can represent my input as x of n. I can represent my channel as some h equivalent of z, and the output as y of n. And now, and of course it is time varying. So if I take a snapshot in time, I get a digital filter. Now, if I tell you equalize it, get rid of the channel impairment, one of the things that you probably have used is 1 by h equivalent of z. That's called a zero forcing equalizer, right? And of course, if you zero forcing has got its limitations, so then you would say, no, I don't want to do zero forcing, I'm going to do MMSC equalization. So again, all of that structure and framework depends on us getting a equivalent representation of the channel. Okay, everyone comfortable with that? So basically, between the input and output, irrespective of the channel, you characterize it as some symbol spaced equivalent channel that we can work with. Okay, Now I am working with a spread spectrum system. So it is no longer symbols that are coming in, chips that are coming in. So what we have in for a direct sequence spread spectrum system is a chip spaced channel model. Chip spaced channel model. Okay, and I'll just pick it up from there, and the rest of it will become very, very easy for you. So we say that the received signal at the receiver is a equivalent of a L+1 tap model, L+1 tap, and this one can be represented as summation L is equal to 0 through L, that's your L+1 taps. The coefficients of the symbol space channel are H subscript L of T times the original transmitted signal. The baseband representation of the transmitted signal was U of T. Now because these are chip spaced shifted versions, this will be T minus LTC. So in other words, what you are representing your channel as a delay of TC, dot dot dot. The first one is H sub 0, the second one is H sub 1, and so on. This is H sub 2. This is how your channel is getting represented, and all of these add together, that's your multipath channel, and this is your output, which is the time dispersed. So this is R of T. And of course you have to add noise to this. So we will add that also, plus Z of T, that's my noise term, plus Z of T. Okay, that's the equivalent channel model that we have. Okay, so let me just take one moment to write this in expanded form, and it actually is helpful for us to look at that in expanded form. So R of T, we have said, consists of L+1 components of the signal. It is H0 of U of T, that's the one without delay, plus H1 U of T minus TC. And the reason it is TC and not some arbitrary tau is because you have taken an equivalent chip spaced channel model. So that's why it makes it very convenient for us to represent H2 of U of T minus 2TC dot 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 plus H subscript L U of T minus LTC plus Z of T, plus Z of T. Now the task for us is to build an optimum receiver. This is my optimum receiver, such that we will just impose the following obvious constraints, that use the information from all the copies of the signal, use information from all copies of the signal, okay, from all copies of the signal, and of course with the intent that you are going to maximize the SNR. And why do we have to add the second condition? Because if one of these taps is very small, no point in giving a lot of weightage to that. So you must make sure that ultimately combining the information gives you maximum SNR. And where did you see this concept before? MRC. So basically it's like reformulate or restating something that looks like the MRC framework, because I have multiple copies of the signal, but by the way they are coming at different delays, but it's okay, the idea is to combine that. Okay, so what I would like to do is to draw for you a structure and then justify that it actually does the optimal combining. So the structure is as follows. So I have a chain of delays, TC, this is delay number 1, delay number 2, all the way to delay number L. And you say, well, this looks like the channel itself. No, there is a slightly different structure that is going to ensue. So I take the first tap, multiply it with G star of T minus LTC, G star of T minus LTC. then followed by an integrator. The integrator, please pay attention to the limits also. I'll write it in a different color so that you won't miss that. It is LTC to LTC plus T. T is the symbol period. It consists, it's equal to Q times TC. Okay, so there are two things. There is Q, which is a spreading factor, which relates T and TC. There are L taps, L plus 1 taps, so just make sure that you are not confused by that. Okay, and whatever is the product of these two is what gets passed through the integrator. You integrate for this period of time. We will call this output as Y subscript L, decision statistic. I'm going to scale this by H of L star and pass it on to a adder. Okay. Now the output of the second branch, and then basically the rest of it repeats, is the same waveform, G star of T minus LTC. The integrator also exactly the same. Exactly the same. Same limits of the integration, integral LTC to LTC plus T, whatever is the product dt, I will call this as YL minus 1, and the multiplier will be H of L minus 1 star, and this gets also gets added. Okay, and just the last one alone. We'll use a different color, use blue. This one also gets multiplied by G star of T minus LTC, followed by an integrator identical. I won't repeat that. The output of this, we call that as Y subscript 0. It's going to be multiplied by H0 star, and this is going to go to the adder. Okay. So now the claim is that this structure is optimum for dealing with the multipath environment that we have just now described. So what are the things to keep in mind? What I would like you to pay attention to, one is the number of taps that are present. It is L plus 1, same as the number of taps of the channel. Okay. Second is the delay of G star, the delay. That's very important, because when you did G star, we have done something to the delay. It's not just G star of T. So delay of G star of T. We have done that. And why does that delay play a role? And the third one is the interval of integration. Interval of integration. All three things sort of have to come together for us to build that. And again, it's very easy. So keep referring to that structure, and let us write down the first output. The first output is integral LTC to LTC plus T, R of T, G star of T minus LTC dt. Am I correct? Okay. And if you go down the order, because the reason it was R of T, because it was there was no delays. If I go further down in the delay chain, that means this dot 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 says along the delay chain, you will get terms of the following: LTC to LTC plus T. It will no longer be R of T, but it will be R of T delayed by some multiple of TC, LTC. But the rest of the expression is the same, G star of T minus LTC dt, and L is equal to 1 to all the way to uppercase L. So basically, these are the outputs that are coming out, and these are the ones that have been designated as the decision statistics as Y0 through YL. So this particular one was designated as YL. Okay. And so basically we look at YL and then quickly generalize to the other terms. So, I'm sorry?
The gain term. H. We've had gain.
Make a mistake?
That is after.
Oh no. Where did I mark Y of L? Did I make a mistake? No, y of L is what
y
I
of L is before-
I do the addition, I will bring the gain term in. Okay, so yeah, so the gain term comes after I get the decision statistic. Okay, so let me just write one term. I think in the interest of time, let me. But I want you to try writing the rest of it. So this expression can also be equivalently represented as 0 to t r of t plus LTC g star of t dt. Okay? Actually, this is a much nicer form for us to work with because, intuitively we like to integrate from 0 to t. So now write down the expression for this. So this will be integral 0 to t, the expression for r of t plus LTC, that is h naught u of t plus LTC plus h1 u of t plus, it's u of t minus tc, so it will be t plus L minus 1 tc dot dot dot, and the last term will be h subscript L u of t, because it already has u of minus LTC and you're going to take r plus t plus LTC. Okay, so this whole thing multiplied by g star of t dt. Okay. Now notice that u of t has got g of t in it. So g of t, g star of t, if I integrate, I will get h subscript L and b root EB. Did I write down the expression for u of t? I think we did, right? No, we have not written the expression for u of t. So expression for u of t is b times root EB times g of t, the pulse shape, and g of t is the spread sequence summation q equal to 0 through q minus 1, c of q, the chip waveform gc t minus qtc. Okay, please, these are the expressions. If you go back, and so now you will get some terms that will be a cross correlation of g of t with some shifted version of g of t. Okay, so basically we will get, this is of course the term that we would like to use for making the decision. What are the other terms? What happens to the noise term? Okay, those are the things that we need to look at, and how is it that a spread spectrum system actually helps us get what we want and throw away or suppress the things that we don't want. And if you have already studied rake receivers, you will know that this is the structure that actually becomes the rake receiver. So what I would like you to do is, if you could try out the expressions that you will get here. When I post it on the website, I'll also give you the how to write these terms. If you can write them, then we can then pick it up from here, and then couple of steps we show how the rake receiver actually emerges from this analysis. So we have a chip spaced equivalent channel which we are trying to use to build an optimal receiver. Thank you.